Something just happened that has astronomers checking their equipment 3 times over. On November 10, 2025, at 0342 UTC, Comet 3I Atlas, an interstellar visitor that's been quietly crossing our solar system for the past 8 months, did something unprecedented. For exactly 4.7 seconds, multiple amateur radio telescopes detected a structured radio pulse emanating from the comet's nucleus, not the random electromagnetic noise you'd expect from ice sublimating in the solar wind. A pulse at 1,420 megahertz, repeating at mathematically precise intervals. And here's what has some scientists privately concerned. That frequency, that specific wavelength, is known in the astronomical community as the cosmic calling card, the hydrogen line, the frequency that any civilization with basic radio astronomy would immediately recognize as artificial. The official explanation came within hours. NASA's Jet Propulsion Laboratory released a statement attributing the signal to natural emissions from cyanogen molecules being ejected from the comet's coma as it heated up during its approach to perihelion. Standard cometary outgassing, they said. Nothing to see here. But that explanation, while scientifically plausible on the surface, doesn't account for 3 critical anomalies that researchers noticed in the data. First, the signal's frequency stability. It varied by less than 0.003 Hz over the entire 4.7-second duration, a level of precision that natural molecular emissions simply don't exhibit. Second, the pulse structure itself contained what radio astronomers call carrier wave characteristics, a fundamental frequency with what appeared to be modulation patterns riding on top of it. And third, perhaps most unsettling, the signal repeated exactly 27 times over the course of 14 minutes before stopping entirely, not gradually fading as the comet rotated or as gas dispersed. It just stopped. Let me give you some context about why this matters. 3I Atlas isn't just any comet. It's only the 3rd confirmed interstellar object ever detected passing through our solar system. The first was Oumuamua in 2017, which famously exhibited acceleration patterns that still haven't been satisfactorily explained by conventional physics. The second was 2I Borisov in 2019, which behaved exactly as a normal comet should, confirming that we do know what natural interstellar comets look like. But 3I Atlas has been different from the start. When it was first detected by the Atlas survey system in South Africa on March 3, 2025, its trajectory immediately raised eyebrows. Unlike most comets, which approach the solar system at angles consistent with random gravitational interactions in interstellar space, 3I Atlas came in at what orbital mechanics specialists call a near-ecliptic approach, almost perfectly aligned with the plane of our solar system, as if it had been aimed. Dr. Elena Rodriguez, an orbital dynamicist at the European Southern Observatory, published preliminary trajectory analysis in June that calculated the probability of such an approach angle occurring naturally at approximately 1 in 2,400. Not impossible, but unlikely enough to warrant attention. What made her paper particularly interesting was the accompanying analysis of 3I Atlas's previous trajectory. By running the orbital mechanics backward through gravitational simulations, her team determined that this object most likely originated from the direction of Alpha Centauri, our nearest stellar neighbor, just 4.37 light-years away. The paper was peer-reviewed, published in the astrophysical journal Letters, and then quietly seemed to disappear from mainstream astronomical discussion. But here's what makes this unsettling. In the 8 months since detection, 3I Atlas has been under almost constant observation by professional and amateur astronomers alike, and the data that's been accumulating doesn't quite fit the profile of a natural comet, even an interstellar one. Its rotation period, measured through brightness variations, is remarkably stable, exactly 11.3 hours, varying by less than 2 seconds over months of observation. Natural comets typically show irregular rotation due to outgassing jets that act like tiny rocket engines, constantly tweaking their spin. 3I Atlas spins like clockwork. Its coma, the cloud of gas and dust that surrounds active comets, has an unusually symmetric structure when imaged at high resolution. Most comets show jets, fans, and irregular patterns driven by active regions on their surface. 3I Atlas's coma is almost perfectly spherical, as if the outgassing is somehow uniformly distributed across its entire surface. And then there's the radio emission event of November 10th. The first detection came from a network of amateur radio astronomers operating in the American Southwest, specifically a collaboration of 12 individuals using home-built dishes ranging from 2 to 5 meters in diameter, all networked together for increased sensitivity. They call themselves the Citizen Sky Survey, and they've been tracking 3I Atlas since August, looking for exactly this kind of anomaly. At 3:42 a.m. Mountain Time, their automated detection software flagged an unusual signal. Within minutes, 3 of the operators were awake and confirming what their equipment was recording. By 4 a.m., they had contacted 2 additional amateur stations in Australia and Chile to verify the detection was real and not some form of terrestrial interference. Here's the critical detail that hasn't been widely reported. The Australian station, operated by retired telecommunications engineer Marcus Chen, recorded the signal at 1420.4057 megahertz, the neutral hydrogen line to within measurement accuracy. This is the same frequency that SETI researchers have been monitoring for decades in their search for extraterrestrial intelligence, specifically because any technological civilization would recognize it as significant. It's the most abundant element in the universe vibrating at its natural resonance frequency. In 1959, physicists Giuseppe Cocconi and Philip Morrison suggested that this would be the obvious choice for interstellar communication, because any species with radio telescopes would be listening to it to study the cosmos. The signal from 3I Atlas hit that frequency like a bullseye. The pulse structure is where things get genuinely strange. Chen's recording equipment, originally designed for satellite communications work, captured not just the presence of the signal, but its fine structure. When analyzed through a spectrogram, a visual representation of how signal frequency and amplitude change over time, the 4.7-second pulse shows 3 distinct characteristics. First, an abrupt onset, rising from noise floor to peak intensity in less than 0.1 seconds. Natural radio emissions from comets caused by interactions between solar wind and the comet's ionized coma show gradual rises and falls. This was like someone flipping a switch. Second, the maintenance phase. For 4.5 seconds, the signal held absolutely steady in both frequency and amplitude. No drift, no variation, no modulation. Then, finally, an equally abrupt termination. But that's just one pulse. The pattern of repetition is what kept these amateur astronomers at their telescopes until dawn. The pulse repeated 27 times, and the interval between pulses was measured by 4 independent stations. The average interval, 31.4 seconds, with a standard deviation of only 0.08 seconds. Think about what that means. Over 14 minutes, this signal repeated with the precision of an atomic clock. Natural phenomena don't maintain that kind of timing. Pulsars do, but pulsars are neutron stars with masses greater than our Sun, rotating at incredible speeds with magnetic fields a trillion times stronger than Earth's. A comet nucleus maybe 10 kilometers across doesn't have the physical mechanism to generate that kind of timing precision. Now, here's where it gets interesting: the direction. Multiple stations used directional antennas to confirm that the signal was indeed coming from the position of 3I Atlas in the sky, ruling out terrestrial interference or satellite signals. But Chen went a step further. Using the Doppler shift of the signal, the same principle that makes an ambulance siren change pitch as it passes you, he calculated that the source was moving at exactly the velocity that 3I Atlas should be moving based on its known orbit. The signal was definitely coming from the comet. But then he did something clever. He analyzed the signal polarization and phase characteristics to determine if there was any directionality to the transmission beyond just away from the comet. Radio waves, like light, have polarization, an orientation to their electromagnetic oscillation. By comparing data from his station with the stations in Chile and Arizona, all separated by thousands of kilometers, he could triangulate the transmission pattern. The signal was beamed, not radiating equally in all directions like you'd expect from a natural source, but focused. And the beam was pointed toward the southern celestial hemisphere, specifically toward a region of sky that contains the constellation Centaurus. Let that sink in for a moment. An interstellar comet, most likely originating from the direction of Alpha Centauri, transmits a structured radio signal on the hydrogen line, beamed back toward the region of space it came from. The same Alpha Centauri system where, in 2020, astronomers detected that controversial candidate signal BLC-1 that caused such excitement in the SETI community before being attributed to terrestrial interference. The same Alpha Centauri that hosts Proxima Centauri b, a potentially habitable planet discovered in 2016, orbiting within the habitable zone of the nearest star to our Sun. The question everyone should be asking is, why isn't this the biggest story in astronomy right now? The Citizen Sky Survey Group did everything right. They documented their observations, shared their data openly, and contacted both NASA and the SETI Institute within hours of the detection. The response was underwhelming. NASA's Near-Earth Object Coordination Office acknowledged receiving the report and stated they would review the data as part of ongoing monitoring efforts. The SETI Institute's senior astronomer, Dr. Seth Shostak, released a brief statement saying that extraordinary claims require extraordinary evidence, and preliminary review suggests natural explanations are more likely. But here's what's conspicuously absent: any detailed technical refutation of the observations. No published analysis explaining how natural outgassing could produce such a precisely timed, frequency-stable signal. No discussion of the beam directionality, just assurances that it's probably nothing. Meanwhile, something interesting happened in the days following November 10th. Multiple professional observatories that had been regularly publishing their observations of 3I Atlas suddenly went quiet. The European Southern Observatory's Very Large Telescope, which had been tracking the comet's spectroscopic signature weekly since July, hasn't released any new data since November 8th, 2 days before the radio event. The Arecibo successor facility, the Green Bank Telescope in West Virginia, one of the world's most sensitive radio telescopes, shows a scheduling gap for 3I Atlas observations during the exact week of November 10th through 17th, despite having had regular observation slots booked for the comet since September. Astronomers who had been actively discussing 3I Atlas on professional forums and social media have suddenly become much more circumspect in their public comments. This isn't speculation. This is documented, verifiable absence of information from sources that had been reliably providing it, and it's creating an information vacuum that's being noticed by the community. Dr. Avi Loeb, the controversial Harvard astronomer who has long advocated for considering artificial origins for anomalous objects like Oumuamua, caught wind of the November 10th event and published a blog post on November 15th titled, "Why We Should Take 3I Atlas Seriously." In it, he makes a compelling argument that the scientific community has a tendency to dismiss anomalous observations that don't fit comfortable paradigms, often before thoroughly investigating them. He points out that the radio observation meets several of the classic criteria proposed by SETI pioneers for what would constitute a potentially artificial signal: narrowband transmission, repetitive structure, frequency stability, and location on a magic frequency that any technological civilization would recognize. He stops short of claiming the signal is definitely artificial, but he asks uncomfortable questions about why there hasn't been more intensive follow-up observation. The official explanation, as I mentioned, attributes everything to natural outgassing, specifically cyanogen molecules. Cyanogen does produce emissions in the radio spectrum as part of complex chemical reactions in a comet's coma, but typically at much lower frequencies, in the megahertz to tens of megahertz range, not at 1,420 megahertz. And those emissions are broadband and chaotic, not narrowband and structured. I've spoken with 2 radio astronomers who work on cometary studies. Off the record, they both expressed skepticism that standard cyanogen emissions could explain what was observed, but neither was willing to go on record challenging the official interpretation. What we know for certain is this. On November 10th, 2025, at least 4 independent stations in 3 different countries detected anomalous radio emissions from an interstellar comet that lasted for 14 minutes, repeated with remarkable precision, and were beamed toward a specific region of the sky. What we don't know is what caused it. Natural outgassing remains possible, but it requires some fairly specific and unusual conditions to explain all the observations. An artificial source, either the comet itself being something other than a comet, or some kind of artificial device embedded within or attached to a natural comet, fits the data frighteningly well, but requires accepting something that would revolutionize our understanding of our place in the cosmos. There's a reason that 1420 megahertz transmission is so significant to this story. When humans have seriously considered how to send messages that would be recognized as artificial by other intelligences, the hydrogen line keeps coming up. It's universal. Any species that studies the universe with radio telescopes will know about it. The first interstellar message deliberately sent by humanity, the Arecibo message of 1974, was transmitted at 2,380 megahertz, but many SETI researchers argued it should have been at 1,420. The WOW signal detected in 1977, still unexplained, was at 1,420 megahertz. Every major SETI program dedicates significant observation time to monitoring this frequency. If you wanted to send a message that would be noticed as possibly artificial, this is exactly the frequency you'd choose. So we have an interstellar object approaching from the direction of the nearest star system, exhibiting unusual but subtle anomalies in its behavior. And it transmitted a structured radio signal on humanity's cosmic calling card frequency, beamed back toward its point of origin. The official explanation is cometary outgassing. Some scientists aren't buying it, but nobody with institutional authority is willing to publicly advocate for a more thorough investigation. Here's what makes this situation particularly urgent. 3I Atlas is not done with its journey through our solar system. Its current trajectory has it making closest approach to Jupiter in March 2026, just 4 months from now. At that point, it will pass within 2.1 million kilometers of the gas giant, well within the orbits of Jupiter's major moons. That's close enough for Jupiter's immense gravity to significantly alter the comet's trajectory. Depending on the exact timing and angle of approach, Jupiter could either capture 3I Atlas into a long-term orbit around the Sun, or it could slingshot the object back out into interstellar space, potentially faster than it came in. Some orbital analysts have calculated that certain scenarios could send 3I Atlas on a trajectory toward the inner solar system, potentially bringing it much closer to Earth than its current orbit. But here's the question that's being quietly asked in certain circles. What if that Jupiter flyby isn't coincidental? What if it's the reason 3I Atlas is here? Think about what Jupiter represents. It's the solar system's dominant planet, containing more mass than all other planets combined. Its magnetosphere, the region of space dominated by its magnetic field, is the largest structure in the solar system aside from the Sun's heliosphere, extending millions of kilometers in all directions. It's been studied extensively by spacecraft: Pioneer, Voyager, Galileo, Juno. We know its composition, its moon system, its radiation environment. If you were mapping the solar system, Jupiter would be the most significant landmark after the Sun itself. And if you were using gravity assists to navigate through the system, exactly like our own space probes do when visiting the outer solar system, Jupiter would be your primary target. The orbital mechanics are interesting. When Dr. Rodriguez calculated 3I Atlas's trajectory backward to determine its origin, she also projected it forward. The nominal trajectory has a close approach to Jupiter in March 2026, but orbital trajectories aren't completely deterministic for objects like comets. Tiny changes in velocity caused by outgassing can alter the path over time. Yet 3I Atlas, despite being active and presumably outgassing, has remained almost exactly on its predicted trajectory with minimal deviation. Its path has been remarkably stable, requiring only minor corrections to the prediction models over 8 months of observation. It's almost as if course corrections are being made to keep it on target, or, more conservatively, as if it's outgassing in such a perfectly balanced way that it's not perturbing its orbit, which would be extremely unusual. Now we come to the March 2026 question. What happens during that Jupiter flyby? The official astronomical community will tell you nothing special. The comet swings by Jupiter, gets gravitationally deflected, probably gets perturbed into a different orbit, and eventually either settles into a long-period orbit around the Sun or gets ejected back to interstellar space. Standard dynamics. This happens with comets all the time. But the alternative hypothesis, whispered about in amateur astronomer forums and discussed in carefully worded terms by researchers who don't want to tank their careers, is much more interesting. What if November 10th wasn't random? What if it was a scheduled transmission, a check-in, a status report, a signal home? The timing is notable, exactly 4 months before the Jupiter closest approach. 4 months is enough time for a return signal from Alpha Centauri to be received, if anyone there is listening and responds immediately. At the speed of light, a round-trip signal to Alpha Centauri takes 8.74 years, but a one-way signal takes 4.37 years. If 3I Atlas sent a message on November 10th, and if something at Alpha Centauri were to respond, that response would arrive in March 2030. But here's the interesting part. We don't know what was encoded in that signal, if anything. The 4.7-second pulse could have contained a tremendous amount of information if it was modulated in ways our amateur detection equipment couldn't resolve. The carrier frequency was obvious. That was probably the point, to get our attention. But the information content remains unknown. Some radio astronomers have suggested that if you wanted to hide a data transmission in plain sight, you'd do exactly what was observed. Put it on a frequency that everyone monitors, make it brief enough that most automated systems would flag it as an anomaly requiring human review, and beam it directionally so that only specific receivers would get the full data stream. Anyone else, like us, would see the carrier but miss the modulation. It's a fascinating idea, but it remains entirely speculative. What we need is better data, which means better observations, and that's where things get frustrating. The astronomical community could settle this fairly easily. Point a major radio telescope at 3I Atlas and watch it continuously for a few weeks. If it's transmitting regularly, we'd see it. If it's just outgassing, we'd see the expected patterns of natural radio emission. The Green Bank telescope could do this. The Very Large Array could do this. The new FAST telescope in China could certainly do this. But as far as publicly available scheduling information shows, none of them are doing this. There's no major radio monitoring campaign announced. No papers in preparation about intensive observation campaigns. Just silence. But we haven't even gotten to the strangest part of this story, because November 10th, while the most dramatic event, wasn't the first anomaly associated with 3I Atlas. It was just the one that finally got noticed by enough people that it couldn't be quietly dismissed. Let me take you back to August 17th, 2025. A graduate student at MIT named Jennifer Kozlov was analyzing archival data from the Hubble Space Telescope as part of her dissertation on cometary coma dynamics. She was specifically looking at high-resolution images of 3I Atlas taken between April and July, trying to map the distribution of gas and dust around the nucleus. Standard work, nothing unusual about it. But she noticed something in the images that didn't make sense. When she stacked multiple exposures taken over several weeks to bring out faint details, she found what appeared to be a very faint, extended structure within the coma that remained fixed in orientation relative to the background stars, rather than rotating with the comet's 11.3-hour spin period. Think about what that means. Everything attached to or part of the comet nucleus should rotate with it. The nucleus is spinning, so any jets, any surface features, any structures connected to it should show that rotation in time-lapse images. But this feature, which Kozlov described as looking like a faint linear structure, almost like a spoke or antenna, maintained a constant orientation. She initially thought it was an image processing artifact, maybe something to do with how she was stacking the exposures. But when she examined each individual exposure, she could see it faintly in the higher quality images. It was real. She wrote up a brief note about it and submitted it to the Minor Planet Electronic Circular, a clearinghouse for observations of comets and asteroids. The submission was acknowledged on August 22nd, and then nothing. It was never published. No explanation, no rejection notice, just silence. Kozlov reached out to her supervisor about the missing publication. According to a Reddit post she made in September, which has since been deleted but was archived by several users, she was told that someone at NASA headquarters had contacted the Minor Planet Center about the submission and requested it be held pending coordination with ongoing observation campaigns. She was told she should wait for guidance before discussing her findings publicly. Being a graduate student dependent on good relationships with the astronomical establishment for her future career, she complied, until November 10th when the radio signal news broke. At that point, she posted her analysis publicly on Archive, the physics and astronomy preprint server, along with her images and data. The paper is still there. You can read it. Anomalous non-rotating structure in the coma of interstellar comet 3I Atlas by J. Kozlov et al. The images are striking. When you know what to look for, you can see it. A faint feature extending from the inner coma outward for roughly 300 kilometers, maintaining its orientation over weeks of observation. Kozlov's interpretation is cautious. She suggests it might be a jet of material being ejected with enough momentum that it remains extended before dispersing, explaining the lack of apparent rotation. But several astronomers who commented on the paper have pointed out that such a jet should still show rotation at the base, where it connects to the nucleus. This one doesn't. Dr. Marcus Webb, a comet specialist at the University of Arizona, posted a detailed analysis of Kozlov's images on his professional blog on November 18th. He notes that the structure's morphology is unlike any cometary feature I've seen in 30 years of studying these objects. He stops short of speculating about artificial origins, but points out that the dimensions and geometry are consistent with a rigid structure of some kind. He concludes by calling for immediate high-resolution observations with the James Webb Space Telescope, which has the sensitivity to definitively characterize the feature. As of today, November 29th, no such observations have been scheduled, at least not publicly. So that's anomaly number 1, a non-rotating structure extending from a rotating comet. Unexplained, observed, documented, and largely ignored by the mainstream astronomical community. Anomaly number 2 came to light through an amateur astronomer's obsessive attention to detail. Thomas Brenner, a software engineer in Germany, has been taking nightly images of 3I Atlas since June using a high-quality amateur telescope and CCD camera in his backyard observatory. Not for any particular scientific purpose, he just finds interstellar objects fascinating. But Brenner is also a programmer, and he wrote custom software to analyze his images for subtle variations in brightness and color that might be missed by eye. On October 3rd, his software flagged something unusual, a brief brightening of the comet's nucleus, lasting approximately 90 seconds, during which the nucleus became about 15% brighter in visible light. It then returned to its baseline brightness. Comets brighten and fade all the time due to outgassing events, so this alone wouldn't be remarkable. But Brenner's software logs everything, and when he reviewed his data for the entire observation period, he found that similar brightening events had occurred on 7 previous occasions: June 24th, July 18th, August 11th, September 4th, September 28th, and October 22nd. They were all approximately the same magnitude, 12% to 17% brightness increases, and all lasted between 80 and 100 seconds. And here's the kicker: they occurred at intervals of 24, 24, 24, 24, 24, and 24 days. Perfect regularity. Every 24 days, like clockwork, 3I Atlas got slightly brighter for about 90 seconds. Brenner posted his findings to the Cloudy Nights Amateur Astronomy Forum on November 12th, 2 days after the radio signal event, suggesting that maybe these brightening events were related to whatever caused the signal. The response was immediate and divided. Some users praised the careful observation and suggested he submit his data for professional review. Others questioned whether his equipment was reliable enough for such precise measurements, suggesting calibration issues or satellite reflections. But then something interesting happened. Another amateur astronomer, Susan Chen in California, no relation to Marcus Chen, who detected the radio signal, posted that she had also observed similar brightening events in her own independent observations. Her dates didn't match exactly with Brenner's. She had less complete coverage, but the two events she had documented fell exactly on Brenner's 24-day cycle. Independent confirmation. The probability of two independent observers both experiencing identical calibration errors that produced false brightening events on the same cycle is essentially zero. This was real. So what causes a comet to brighten by 15% for 90 seconds every 24 days with perfect regularity? The most generous natural explanation would be some kind of outgassing event triggered by subsurface heating as the comet approaches the Sun. But such events should increase in frequency and intensity as the comet gets closer and receives more solar heating. These events maintained constant periodicity and magnitude over 5 months, spanning a significant change in solar distance. And why exactly 24 days? That number seems arbitrary from a natural physics standpoint, but it's suspiciously human meaningful. Exactly 1/5 of the period between events would be… No, I'm getting ahead of myself. That's anomaly number 2, periodic brightening on a precise 24-day cycle. Observed, confirmed, unexplained. Anomaly number 3 is the most technical and perhaps the most difficult to dismiss with conventional physics. Dr. Harold Kim, an astrodynamicist at the Jet Propulsion Laboratory, has been analyzing the precise trajectory of 3I Atlas using astrometric data, basically measuring its exact position in the sky over time from multiple observatories. This is routine work for tracking potentially hazardous asteroids and comets. You need very precise position measurements to predict future trajectories accurately. But when Kim ran the standard models for 3I Atlas's orbit, he found discrepancies. The comet wasn't exactly where it should be based on pure gravitational dynamics. It was off by tiny amounts, fractions of an arcsecond on the sky, but consistently off in ways that couldn't be fully explained by the expected effects of outgassing. This is where it gets technical. When a comet outgasses, the jets of gas act like tiny rocket engines, pushing the nucleus in various directions and slightly altering its trajectory. This is called non-gravitational acceleration, and it's well understood. There are standard mathematical models for it based on the comet's rotation, activity level, and distance from the Sun. Kim applied these models to 3I Atlas and found that they couldn't fully account for the observed trajectory deviations. The residuals, the differences between prediction and observation, showed a pattern. The comet appeared to be experiencing small accelerations perpendicular to its direction of motion, in pulses, roughly every 23 to 25 days. Kim presented his preliminary findings at the American Astronomical Society's Division for Planetary Sciences meeting on October 9th. His talk was titled Anomalous Non-Gravitational Accelerations in Interstellar Comet 3I Atlas. In it, he carefully documented the trajectory discrepancies and noted that the timing of the acceleration events, while uncertain due to the coarseness of the astrometric data, appeared to correlate with something periodic. He didn't speculate about causes, but in the question period after his talk, someone asked whether the accelerations could be consistent with attitude control thrusters firing. Kim's response, according to attendees who posted about it online, was cautious. He said that the magnitude and direction of the accelerations could be consistent with small thrust events, but that he had no evidence that's what they were, and that natural outgassing remained the most likely explanation. He also noted that more precise tracking data would be needed to definitively characterize the accelerations. The timing correlation between Kim's astrometric anomalies and Brenner's brightness events is striking, both on roughly 24-day cycles, both showing consistent magnitudes. Is it possible that the brightness events are caused by, or correlated with, whatever is producing the trajectory anomalies? If you were operating a spacecraft disguised as a comet, you might periodically need to fire thrusters to maintain your desired trajectory. Those thruster firings would produce both a small acceleration, detected astrometrically if you're measuring carefully enough, and potentially a brief brightening, the thruster plume catching sunlight. The duration, 90 seconds, would be consistent with a minor course correction burn. This is, of course, pure speculation, but it's speculation that fits the observations remarkably well. That's anomaly number 3. Non-gravitational accelerations on a periodic cycle matching the brightness events. Documented by a JPL scientist, presented at a professional conference, and largely uncommented upon by the broader community. Anomaly number 4 takes us back to the object's discovery and raises questions about what we're being told. When 3I Atlas was first detected on March 3, 2025, the discovery was announced by the Atlas Survey System, the Asteroid Terrestrial Impact Last Alert System, a NASA-funded program that scans the sky nightly looking for potentially hazardous objects. The initial announcement described it as a probable long-period comet with an unusual orbit requiring further observation. Within 48 hours, follow-up observations from multiple observatories confirmed that the orbit was hyperbolic, meaning the object came from interstellar space, and the designation was changed to 3I Atlas, the third interstellar object. But here's what's interesting. The Atlas system's discovery images show 3I Atlas as a moving point of light, as expected. However, some amateur astronomers who have carefully examined the publicly available discovery images have noted that the object appears to have been slightly brighter in those earliest images than would be predicted based on its distance from the Sun and its subsequent brightness evolution. Specifically, Pavel Novak, a Czech astronomer with experience in photometric analysis, calculated that if you extrapolate backward from the well-characterized brightness measurements taken from April onward, 3I Atlas should have been about 0.3 magnitudes fainter on March 3rd than it actually appeared in the discovery images. That's a factor of about 1.3 times brighter than expected. Novak published his analysis on his blog on November 20th, suggesting that the comet might have been experiencing an outburst during discovery, a sudden temporary increase in activity. But outbursts typically last hours to days, not the multi-week period that would be required to explain the brightness evolution in this case. The alternative, which Novak mentions but doesn't endorse, is that something about the object was different during discovery. Perhaps it was more reflective or larger, or had some kind of feature that was subsequently retracted or changed. He calls for the Atlas team to release the raw discovery images for independent analysis, but as of now, only the processed, reduced images are publicly available. Why would an interstellar object be brighter during its discovery observation than it should be based on subsequent behavior? There's no obvious natural explanation. It's a puzzle piece that doesn't quite fit. That's anomaly number 4, unexplained excess brightness during discovery, suggesting the object may have changed between first detection and subsequent observations. Anomaly number 5 is perhaps the most speculative, but it's been discussed extensively in radio astronomy circles since November 10th. It involves the question, was November 10th the only transmission? Marcus Chen, the Australian radio astronomer who captured the best data on the November 10th signal, has been continuously monitoring 3I Atlas since then, hoping to detect additional transmissions. He hasn't found any, but that's not the interesting part. The interesting part is what he found when he went back through his archival data from earlier observations. Chen has been casually monitoring various solar system objects, including 3I Atlas, since August as a hobby project. His equipment automatically logs all data, even when he's not actively watching it. When he went back through those logs after November 10th and applied the same detection algorithms he used to identify the November signal, he found 3 potential earlier events. Brief, narrowband signals at or near 1,420 megahertz, lasting a few seconds, coming from the direction of 3I Atlas. The events were on September 13th, October 7th, and November 3rd. They were much weaker than the November 10th signal, barely above the noise threshold, and Chen initially thought they might be just statistical flukes in the noise. But their timing is suggestive. September 13th to October 7th is 24 days. October 7th to November 3 is 27 days. November 3 to November 10th is 7 days. The pattern isn't perfect, which is one reason Chen has been reluctant to claim these as real detections. But if they are real, they suggest that November 10th was not an isolated event, but rather the latest and strongest in a series of transmissions that have been occurring roughly every 24 to 30 days, the same periodicity as the brightness events and astrometric anomalies. Chen has posted his tentative findings on his personal website, clearly labeling them as preliminary and unconfirmed, and he's called for other radio astronomers to search their own archival data for similar signals. As of now, no one else has publicly reported finding anything, but that might simply mean no one else was looking at the right frequency at the right time. If these earlier signals are real, it would strengthen the case that something systematic is happening with 3I Atlas. Regular transmissions, regular brightening, regular trajectory corrections, all on roughly the same cycle. That's a lot of coincidence. That's anomaly number 5. Possible earlier radio transmissions on a similar periodicity, detected but unconfirmed. Now, let me be clear about something. None of these anomalies individually proves anything extraordinary. Each one has potential natural explanations, even if those explanations require some special pleading or coincidence. Outgassing can do weird things. Comets can have unusual structures. Measurement errors and calibration issues can create false patterns. The scientific principle of parsimony, Occam's razor, says we should prefer the simplest explanation that fits the facts. And the simplest explanation is that 3I Atlas is a natural interstellar comet that happens to be behaving in some unusual but ultimately explicable ways, and that November 10th was a coincidental radio emission from natural processes that happen to occur on a frequency significant to human SETI researchers. But here's where conventional science gets uncomfortable. When you have 5 separate anomalies, all occurring in the same object, all exhibiting roughly the same periodicity, all unexplained by standard models, at what point does the accumulation of coincidences become more implausible than the alternative hypothesis? Some researchers are quietly asking that question. Dr. Avi Loeb is the most public, but he's not alone. There are others, tenured professors at major universities, senior scientists at research institutions, who are privately expressing concern that the astronomical community is not taking 3I Atlas seriously enough. The stigma associated with suggesting artificial origins for celestial phenomena is powerful. It's career-ending for junior researchers and reputation-damaging even for established scientists. So most stay silent, or couch their concerns in extremely careful language, or publish their observations without interpretation and let others draw conclusions. But the Whisper Network exists. Conversations at conferences, private emails, off-the-record discussions with journalists. There's a growing sense among some astronomers that 3I Atlas might be something we need to investigate much more thoroughly than we are. And there's frustration that the major institutions, NASA, ESA, major observatories, seem uninterested in mounting the kind of intensive, coordinated observation campaign that would be warranted if there were genuine uncertainty about the object's nature. This brings us to the question of information control. I want to be careful here because we're moving from documented observations into the realm of inference and pattern recognition. But there are some facts that are publicly verifiable. We know that the European Southern Observatory stopped releasing spectroscopic data on 3I Atlas after November 8th, despite having maintained a regular observation cadence for months prior. Their observing schedule for the VLT is public, and there's a gap where you'd expect to see continued 3I Atlas observations. When journalists inquired about this, the official response was that the data was undergoing quality review and would be released in due course. That was 3 weeks ago. Spectroscopic data processing doesn't usually take 3 weeks. We know that the Green Bank telescope, which has been used for SETI observations and is the most capable radio telescope in the Western Hemisphere, shows no publicly scheduled observations of 3I Atlas, despite the November 10th event. GBT's observation schedule is partially public for scientific transparency. Gaps in that schedule typically indicate either maintenance periods or classified observations. The telescope is occasionally used for radar observations related to satellite tracking and national security, during which time the schedule is not published. There's been a scheduled gap around 3I Atlas's position for the past 2 weeks. We know that Jennifer Kozlov's paper about the anomalous structure was initially blocked from publication, though it's now available on archive. We know that Harold Kim's trajectory analysis was presented at a professional conference but hasn't been submitted for peer-reviewed publication, despite being exactly the kind of careful analysis that would normally result in a journal paper. Individually, these could all be coincidences or routine administrative issues. Together, they paint a picture of information that's being controlled more carefully than is typical for astronomical observations. Why would that be? There are two possible answers. The boring one is that the astronomical establishment is being cautious because they're concerned about public overreaction to inconclusive data, especially given the media circus around Oumuamua and the conspiracy theories that generated. Better to stay quiet until they have definitive answers. This is reasonable, even if it's frustrating for those of us who think the public deserves to see the data and make up their own minds. The more concerning answer is that someone, somewhere, has data that we don't have access to. Data that suggests 3I Atlas is something that requires a coordinated response. Data that would cause significant public concern if released without proper context and preparation. This is more speculative, but it's worth considering. Major observatories and space agencies have the capability to observe 3I Atlas in ways that amateur astronomers cannot. Infrared spectroscopy that could definitively determine surface composition, radar observations that could map the nucleus in detail and identify any artificial structures, intensive radio monitoring that would detect any additional transmissions. If such observations have been conducted, and if they've revealed something extraordinary, there might be legitimate reasons for careful control of that information while decision-makers figure out what to do about it. I'm not claiming there's a conspiracy. I'm noting that there's an information gap, and that gap is larger than is typical for astronomical discoveries of this significance. An interstellar object is inherently interesting. An interstellar object showing multiple unexplained behaviors is even more interesting. The level of public information available doesn't match the level of scientific interest you'd expect, and that asymmetry raises questions. Now let's talk about what comes next, because March 2026 is rapidly approaching. The Jupiter flyby will be the most dynamically significant event in 3I Atlas's journey through our solar system. Jupiter's gravity will either capture the object into a long-term orbit or eject it back to interstellar space. The exact outcome depends on the precise trajectory, which in turn depends on those small, non-gravitational accelerations that Harold Kim documented. Minor course corrections now could mean the difference between ejection and capture. If 3I Atlas is natural, the flyby is just interesting orbital dynamics. If it's artificial, if it's some kind of probe or vessel, then the Jupiter flyby might be the entire purpose of its mission. What could you learn from a close pass of Jupiter? Everything. Its magnetic field topology, its radiation environment, its atmospheric composition at depth, its internal structure inferred from gravity measurements, its moon system, its ring system. The Juno spacecraft has been studying Jupiter for years, but it's in a polar orbit that doesn't allow it to study certain regions in detail. A close flyby on a different trajectory could provide complementary data that would fill gaps in our understanding. Or, if you want to get really speculative, a Jupiter flyby would be an excellent opportunity to deploy something. A sub-satellite, a probe, a communications relay, something that could remain in Jupiter orbit after the main craft continues on its journey. The mass of such a payload would be tiny, maybe a few kilograms, and completely undetectable from Earth at the current distance. If 3I Atlas is carrying any kind of payload intended for deployment, we wouldn't necessarily know until it happened, and by then it would be too late to do anything about it, not that we could do anything anyway at that distance. This scenario, interstellar probe deploys satellites during planetary flybys, is not original to me. It's been discussed in the scientific literature on interstellar exploration for decades. It's one of the proposed architectures for how an advanced civilization might explore the galaxy efficiently. Send small, fast probes that visit multiple star systems, using gravity assists to navigate, deploying sensor packages at interesting locations, and transmitting data back home. The whole system runs autonomously because round-trip communication times are measured in years to decades. Our own Voyager probes are primitive versions of this concept, though they're not deploying anything and they're barely making it out of the solar system. If that's what 3I Atlas is, a survey probe conducting a grand tour of our solar system, then November 10th makes perfect sense. It's a status report. Solar system entered successfully. Inner system surveyed. Primary objective, Jupiter approaching. Trajectory nominal. Beam it back home. If the mission plan includes satellite deployment at Jupiter in March, then anyone back home would want to know the mission is on track. 4 months of warning before the critical event. That timing works. But let's step back from speculation and consider what we should be doing, regardless of 3I Atlas's true nature. The obvious answer is, observe it intensively. Point every capable telescope at it. Radio, optical, infrared, ultraviolet. Continuous monitoring from now until well after the Jupiter flyby. Map the nucleus at the highest possible resolution. Characterize the coma spectroscopically. Monitor for any additional radio emissions. Track the trajectory with extreme precision. If it's natural, we'll learn a tremendous amount about interstellar comets, which are important for understanding planetary system formation and the transport of organic materials through the galaxy. If it's artificial, well, that would be the most important discovery in human history. The fact that we're not doing this, at least not publicly, is baffling. Unless we are doing it and it's just not being discussed, which brings us back to the information control question. There's a broader philosophical implication here that's worth considering. If 3I/Atlas is artificial, what does that mean for humanity? It means we're not alone, which most people probably already suspected. It means another technological civilization exists, or existed, in our cosmic neighborhood. It means they've developed interstellar travel capability, at least for small robotic probes. It means they're curious about other star systems, just as we are. These are profound realizations, but they're not necessarily threatening. A civilization capable of sending probes to other star systems is, by definition, advanced. But advanced doesn't mean hostile. The probe hasn't done anything aggressive, it's just looking around, collecting data. Same as our probes do when we send them to other planets. The more interesting philosophical question is, what do we do with this knowledge? If 3I Atlas is confirmed to be artificial, does humanity try to communicate with it? Attempt to rendezvous with it somehow? Try to retrieve it for study? Or do we just watch it complete its mission and leave? These are questions that would need to be answered at the highest levels of global governance, which is probably why, if any of this is true, information is being controlled so carefully. You don't want premature public panic or excitement before there's a clear plan. But here's the thing, the public deserves to know. We deserve to be part of this conversation. This is humanity's moment, not just the astronomical establishment's moment or any single government's moment. If there's genuine uncertainty about what 3I/Atlas is, that uncertainty should be shared. If there's data suggesting something extraordinary, that data should be released so the global scientific community can collaborate on understanding it. Science works best when it's open, when data is shared, when multiple perspectives can contribute to interpretation. The pattern of information restriction we're seeing, tentative though it is, suggests that someone, somewhere, has decided that openness is not the right approach here. That decision may be well-intentioned. They might be waiting for more definitive data before making announcements. They might be concerned about public reaction. They might be coordinating with other agencies and governments to prepare a unified response. All of these would be understandable motivations, but they're also paternalistic. They assume that the public can't handle ambiguity, that we need to be protected from incomplete information, that we'll panic or respond irrationally. I don't believe that. I think most people are perfectly capable of understanding that science sometimes produces uncertain results, that we can observe something anomalous without knowing exactly what it means. That we don't know yet is a legitimate answer, and I think the credibility of scientific institutions depends on being transparent about uncertainty, not hiding it behind wait for more data stonewalling. So here we are, 11 days from December, with 3I Atlas continuing its journey inward toward Jupiter, exhibiting behaviors that are puzzling but not definitively artificial, transmitting radio signals that are anomalous but not definitively intelligent, showing structural features that are unusual but not definitively technological. The data is tantalizing but ambiguous. The official story is, it's probably natural, stop worrying about it. The alternative story is, maybe we should look at this more carefully. And somewhere in between those two positions is where the truth lies. What happens next depends on what 3I/Atlas does or doesn't do over the coming months. If it remains quiet, if the anomalies don't repeat or can be explained by refined models, then this will fade into astronomical history as that weird interstellar comet that got people excited for a while. If it transmits again, especially if it does so on a predictable schedule, the case for artificial origin becomes much stronger. If it does something unexpected during the Jupiter flyby, trajectory changes that can't be explained by gravity and outgassing, detectable emissions, any kind of payload deployment, then we'll know for certain. Until then, we watch, we wait. We hope that someone with access to better instruments is watching more carefully than we are. And we remember that November 10th, 2025, the day an interstellar comet transmitted a radio signal on humanity's cosmic calling card frequency, beamed toward the constellation Centaurus, the constellation that contains Alpha Centauri, the nearest star to our Sun, the star this object most likely came from. Maybe it was just outgassing. Maybe cyanogen molecules can do things we don't fully understand. Maybe every anomaly has a natural explanation that we just haven't worked out yet. Or maybe, just maybe, something from another star system is surveying our cosmic neighborhood, and on November 10th, it checked in with home. Solar system traversed. Next target, Jupiter. Satellite deployment, March 2026. We'll know in 4 months. Watch the skies. Pay attention to what's not being said as much as what is. Keep asking questions, because whether 3I Atlas is a comet or a probe, whether its radio signal was natural or artificial, whether March 2026 brings routine orbital mechanics or first contact, this matters. This is our moment to confront the possibility that we're not alone, and how we handle that possibility, with curiosity, with skepticism, with openness, with honesty, will say a lot about who we are as a species. The hydrogen line frequency, 1420.4057 megahertz. The cosmic calling card. If someone wanted to get our attention, that's exactly where they'd transmit. And on November 10th, for 4.7 seconds, repeated 27 times over 14 minutes, beamed toward Alpha Centauri, that's exactly what 3I Atlas did. Coincidence? You decide.